Welcome back to day 3 of the lead tutorial. So I thought of yet another thing that I should do. So the proposal was that we start thinking about writing down interesting theorems that one might try to prove. But then it occurred to me, it's highly likely that anything we might want to write down will require some kinds of algebraic structures. We're talking about vector spaces or some algebraic number field and so on. And so it occurs to me that I need to tell you about how algebraic structures work in lean. So this is something that if you're focusing on IMO problems, you can focus on just integers and concrete structures and the reals. But once you get to university level mathematics, that's when you start, mathematics students start looking at modern algebra groups and rings and fields and order structures and partial orders and lattices. And on the analysis side, there's metric spaces and topological spaces. And lean also has uniform spaces. You start doing measure theory and probability. There are measure spaces and probability measures. In analysis, there's Hilbert spaces and Banach spaces and norm topological spaces and norm algebraic structures. There's manifolds. And all these things are in MathLib. There are also categories and sheaves and toposes or topoi. And then and a lot of the successes of lean have gone towards building even more elaborate algebraic structures on top of that. So we have perfectoid spaces, whatever they are. Just this morning on Zoom, on Zulip, Johan Komelin announced that we're close to having a topology, whatever that is, and smooth morphisms of schemes. And, so there's a lot of stuff there, and I want to give you a sense of how that works. Okay, so on the screen, what you're looking at is a simple proof that x plus y squared equals x squared plus 2xy plus y squared. And that's something that the ring tactic will do automatically. So it's just a one-line proof. But then you might think, well, this identity should hold more generally. It's not just, for example, it'll hold in the integers. So one thing you might try is let's generalize this to an arbitrary type R and see what kind of structure we need on R. Okay, so here the proof breaks right away because just saying that R is an arbitrary type doesn't lean can't make sense of addition. Let's try telling lean that R is a ring. So that's what I just did by writing this annotation in square brackets, ring R.
Why is it there as opposed to the line above where you're declaring R?
Oh, I could put it there. Sorry.
Okay.
That is actually a more natural place to put it. I'll put it there. Yeah, so putting the arguments in a different order still didn't hurt. It could still find it, but you're right, it's more natural to group it with the structure. And that still doesn't work. You get an error message and ring says try ring NF, but if we try ring NF, still nothing happens. So let's go back to ring. The thing is, for this to work, you need that the ring is commutative. Okay, so if we go to com ring, all of a sudden now we have a more general theorem, right? The reals are an instance of a com ring. So in particular, the identity proved will hold for the reals, but we've proved it in more generality. And in fact, the identity doesn't need the fact that you have subtraction. So in fact, slightly more generality, we can generalize it to a com semi-ring. And so that's the idea. In lean and MathLib, we try to prove things at the most natural level of generality.
This is kind of a reverse tactic. Would have told us to make this proof work, what structures would have sufficed.
There isn't. So that would be maybe that's a good machine learning challenge, or to try to kind of guess structures. Yeah. And so typically people will do it by hand and try. It will, to some extent, the tooling will tell you when you have a hypothesis that you don't need. And so you often get a linter message that will let you strengthen the theorem, and that can be improved as well. But no, for the most part, these kind of experiments are done just by messing around by hand. Yeah, so what I want to show you is that there's a lot going under the hood that, even, so we've used things like, MCOM and, mul, so. And if we look more carefully at the annotation of MCOM, it says for any type G that has the structure of being a COM magma, whatever that is, if A and B are in G, A times B is equal to B times A. I mean, what that really says is, the identity MCOM, it holds wherever it holds. And the point is, you can use it anywhere that it makes sense, and Lean will figure out. So a COM magma just happens to be a structure with a binary operation that's named times, and that's commutative. It's just kind of a trivial structure, but that's all you need for the identity to hold. And so now, if you say check MCOM, if you apply MCOM to X and Y, it tells you that X times Y is equal to Y plus X, so it instantiated the theorem. But X and Y are elements of a type R that has a COM semi-ring structure. And so somewhere in there, Lean has to figure out that being a COM semi-ring means inheriting the structure of a COM magma. And you can see that happening if you say set option PP. So I'm telling Lean to basically pretty print everything, just turn off all the hidden arguments and notation and so on, and just show me everything. And so when you type MCOM XY, I mean, you've typed MCOM XY, this is what Lean sees. This is what MCOM XY parses to. This is kind of the full expression. And so if you remember, the first argument to MCOM was the data type R, but the second one was supposed to be the instance of the COM magma. And so here, what's going on is, so it knows that R is a COM semi-ring, that's this inst, but it knows that every COM semi-ring is a non-unital COM semi-ring. And it knows that every non-unital COM semi-ring is a COM semigroup, and it knows that every COM semigroup is a COM magma. And so, of course, that's why you can use this. And it gets even worse than that. So MCOM X and Y, says something about X times Y, and so the question is, where does this times come from? Again, there's a story here. I mean, this is the expression that X times Y equals Y times X. So that's where the equals is. That's an equality. But this expression here that I'm kind of hovering over is just the X times Y. And it's figuring out what the multiplication is. I mean, that, those lines, those 1, 2, 3, 4, 5, 6, 7 lines are just the expression X times Y. But to make sense of it, the multiplication, I mean, there's at the bottom is the X and the Y. So this is the thing that names the multiplication. But basically, because R is a COM semi-ring, it's a non-unital COM semi-ring, and hence a COM semigroup, and hence a COM magma. And every COM magma has a multiplication, and that's the multiplication that you mean when you write X times Y. And to me, this is one of the great feats of engineering of Lean, that you can write MCOM X, Y, and be totally oblivious to all this, but somehow Lean is running around under the hood and filling in all this information. So Lean uses a mechanism called type class inference. Oh, and I wanted to say that, so the place to read more about this is once again Mathematics in Lean. So I said, I told you that, with students in the undergraduate class I'm teaching, we spend the first half of the semester working through all the fundamentals. And so, the last couple of days, we've done things in chapters 2 and 3. If we were to move on after that, we'd be doing sets and functions and, function images and unions and intersections. We've seen a couple of proofs by induction. But then, we're about halfway through the book, with structures and hierarchies. It's these sections that talk about the handling of algebraic structures that I'm just kind of giving you a quick overview of. But so Lean uses for this a mechanism called type class inference. And I just want to spend a minute to kind of try to convey how impressive the engineering feat is by just sort of giving you a sense of the size or the scale. So every algebraic structure is represented as a type class. And type classes are slightly more general. They're used for lots of things that you don't really think of as being algebraic classes. But in Lean, I mean, last time I checked, there were more than 1,500 classes, and more than 20,000 declared instances between those classes. And if you want to think of this as something like an algebraic hierarchy diagram where there are like 15,000 nodes and kind of 20,000 arrows, telling you what's an instance of what, you're not too far off. I do have a picture here of so these are the type classes that really are more like algebraic structures, in the sense that there's kind of a data type and there's a structure on it. And so this is kind of a more manageable portion of the the algebraic hierarchy. But it looks like this. And if we zoom in, we can kind of look around and see. So there's a normed ordered group, looking for things that might look familiar. Ordered COM monoid, canonically ordered COM semi-ring, the distributed lattice, a complete linear order, the Boolean algebras and complete Boolean algebras. Kind of zooming around, what else? What other fun things can we find? Cancel semigroups. There's measurability, measurable multiplication, involutive, cancel monoid with zero COM group, normalized GCD monoid, semi-field, Boolean rings. So here's some ring theoretics. There's rings, commutative rings, domains, integrally closed rings, Dedekind domains, local rings. Let's see, then some of the analysis of this topological group. Let's see, where do we have topology, or this connected space. Somewhere there's like the T0, T1. There's some category theory. There's measurable. There's topological rings. Yeah. So I guess the point is that there's C-star rings. So the point is that there's a pseudo E metric space. So that would be something like a metric space, but it can take values at distances of infinity. And the pseudo will be presumably that you can have things that have distance zero but are not equal. So it's maybe or pre-metric space. Polar spaces, T2 spaces, T1 spaces, quasi-sober spaces. There's some category theory stuff. So there's really just a tremendous, there's a tremendous amount of stuff there. Another way I like to, kind of convey kind of the scope is if you go to the lead proof of community pages, the API documentation. So with common structures like the real numbers, let's find the real numbers. One of the things you can do is you can ask Lean, tell me all the things that that MathLib declares the reals to be instances of. Structure real. And so I don't know what all of these things are, but let's see. There should be COM ring somewhere. Matrix small ring. Yeah. So the reals are a commutative ring. They're a field. They're COM monoid. They're but then they're more. So they're uniform COM space. They're locally convex space. They're ordered topology. Yeah, so there's lots of crazy structures. And similarly, if you do the integers, you can find more exotic.
Why don't you show us the definition of one of these structures just to get a sense of?
Oh, do you? So yeah, you can click on it. So I don't know.
Some structure that you can add.
So it's a div in. So this says, what does it say? Div in monoid. So if M is a, I don't even know what this means. It says that if M is a monoid with a division on it, then maybe the MC, I don't know. Maybe M is a structure that you can, this might just be a notational thing that you can write M to the N where N is any integer. I think it's probably that, so that there is an instance of a power operation, with elements of M in the integers. Yeah, let's see if we can find a more interesting one. Well, so there's Euclidean domain. That's a more familiar one.
So does that tell us? How does one think about that?
Oh, one or more equations are not get rendered due to their size. What's going on there? Okay. So what's going on here? So Euclidean domain. Oh, so this is just the declaration of the instance, that the integers are an instance of a Euclidean domain. Right? And if you want to see what a Euclidean domain is, that's there. And these are all, and it looks like there's a lot of extra stuff in here, and later we can talk about why that's there. But if you jump to the definition of a Euclidean domain, it's a commutative ring. It's a non-trivial commutative ring, and yeah, and it extends it, and basically taken all together, these are all the things that you have, axiomatically when you have a Euclidean domain.
So some of these could be like operations or functions.
There are operations and the properties of the operation. And so it looks like you're being redundant, that you have the negation and the subtraction, right? But for reasons that we can talk about later, it turns out to work better to say that you have a negation and subtraction. And the subtraction should have the property that a minus b should be equal to a plus negative b. And that gives you, when you instantiate it, that gives you the option of, you can either define, by definition, the subtraction to be exactly that, or you might define subtraction some other way and just prove that it.
And then these are like the general attributes, and then when you say the integers are an instance of this,
you get all of exactly. You have all of those.
You have to tell it how to do.
No, you just once you can infer that the integers are an instance of that. Okay. You have all of these things, and any theorem that's proved for any Euclidean domain, and any theorem for any structure that inherits, the properties of the Euclidean domain. Yeah. And the other way you can go is, rather than look at the concrete instances and some of the things that it's an instance of, you can say, here's a COM ring. Show me things that are instances of a COM ring. And so every Boolean ring is a commutative ring. If you take the Cauchy completion of a commutative ring, so presumably it's a commutative ring that has some notion of some metric, some notion of distance. But if you take an appropriate completion of a commutative ring, you again have a commutative ring. I think this means that the complex numbers are a commutative ring, and so on and so forth. So
maybe it would be helpful to pick some simple one-order theorem that actually uses a structure in a non-trivial way, and we can see.
Yeah, so let's head in that direction. Okay, so let's talk about actually using this. So I think part of the challenge is that when you decide to do something algebraic, you have to figure out what the classes are and what the intended ways of using them are, and it can be sort of non-trivial. So I mean, suppose you said to me, okay, what I want to do is let's formalize some statement about a vector space, right? So you need to know that, okay, so if you're talking about a vector space, you're talking about a vector space over some field, and now you need to figure out the magical incantations to tell Lee that you want to reason with a vector space over a field. And it turns out this is how you do it. So first of all, so you want to say, when you're saying variables, so you want to declare variables, data types for your vector space in your field. And then you want to say that, F is a field. And then, so this is the confusing part. So you want to say that V is an add COM group or COM add group. So it's add, wait, oops, sorry. No, I was right, add COM group. And then what you want to do is you want to say that V and F together have the structure of a module. So you want to say module V. Yeah, that works. Right. So what you do, you're declaring in pieces. You're saying you have a field, you have the underlying set of the vector space, which is added commutative group, and then there's a scalar action of F on V, a scalar multiplication satisfying the appropriate limits. And so this works if I change field F to, ring F or ring R. You can declare a module over a ring. And then you just sort of have to remember that a vector space is just a module over a ring that happens to be a field. And so, this is just the API. And so any library in linear algebra will start having some vector spaces in the field and so on, and we'll declare them that way. And you just have to know that, right? Or get used to it. And so in a moment, I'll talk about how you start figuring these things out by looking around Mathlib and looking at examples. But just to give another example, so in linear algebra, most linear algebra is done kind of abstractly and axiomatically. So you've got, vector spaces and linear maps and so on. But, sometimes you want to deal with the coordinate version. I mean, you want to talk about bases and matrices and vectors and so on. And Lean has all that as well. And, the connections between, you have a matrix, it gives you a linear map and so on. What did I say? Oh, so suppose you want to talk about and even just say an m by n matrix over the real numbers. So the way to do it is to say variable. So let's make m and n natural numbers. Right, and so now I want to say matrix over. So let's say M be an m by n matrix. So it turns out the way to do it is you say fin m, or fin n, say n by m, so fin n, fin m. Let's say over the reals. Okay, so this is the magical incantation. So you're saying I've got a matrix with real number entries where the rows are indexed by fin n. So those are just the numbers 0 to n minus 1. And the columns are indexed by the numbers from 0 to n minus 1. Right, so even just knowing how to say n by n or m by n, maybe n by n, to say m by n matrix, that's tricky. But then you should know that this is actually probably not the way you want to state your theorem. Okay. So in Mathlib, the general convention is that when you deal with matrices, the point is that it doesn't matter what you use to index the rows and columns. I mean, 1 to n or 0 to n minus 1, those are common choices, but you can really index it with, well, any set for an infinite matrix. If you want to do sums and so on, you need to know that they're finite, they're finite indices. And it turns out that the extra generality, stating things in that greater generality, is useful. I mean, the problem is that, if you have, a vector index from 0 to n minus 1, and then another one indexed from 0 to m minus 1, and then you concatenate them, then you're adding offsets and subtracting, and every time you reason about the relationship between the two, you're doing a little bit of arithmetic, and it's a pain in the neck. And you can just as well just kind of use the direct, so if you have just arbitrary indexing sets, you can just use the direct sum of the indexing set to index that, and it just turns out to work better. And so, the Mathlib convention is to instead say, so here's the magical way that you say that U and V are kind of finite indexing types. So you say U and V are types, and then you say that they're fin types. Oops. And again, it'll take me some while to explain fin types and fin sets, but the way to interpret this is just those extra annotations just say that U and V are finite. And so, the preferred, let me just copy this, the kind of preferred way to state your theorems when you can, when the indexing set really doesn't matter, is variable, is just to say that, M is a, UV matrix, right? It's a matrix, indexed by U and V. And if you look at matrix composition, it'll do exactly that. It'll say, given any fin types U, V, and W, and a U, U by V matrix, or V by W, you give it U by W, the multiplication, and so on. And so, yeah, so a lot of the challenge of even just learning to state things is just understanding the idioms.
Can we step back a bit? Again, there's a lot to cover, and I don't want to spend a lot of time, but so, I mean, certainly this combines many points. And for example, the lesson that it's better to use a general finite set than to restrict your indices to 0, 10, or whatever is a good one that many people know. And then there's many other choices here. And I guess my meta question is, does anybody kind of step back and say, were these really the best choices we could have made, going forward?
So the wonderful thing about Lean and MathLib is that it's constantly being rewritten and refactored, and people will, even at the expense. I mean, this is hard, kind of for when you build on MathLib. Every time a fundamental change happens to MathLib, lots of things break in MathLib, and a lot of the basics have kind of settled by now. I mean, I think the integer, even theorems about the integers get renamed, every once in a while, and so on. But the community doesn't hesitate to refactor and improve when a couple of years down the line, and with the you can look back and say, oh, this is how we should have done it, and people will go back and make these changes. So so things are constantly changing. When people are constantly going back and saying, is there a better way to do this?
Well, that's a good answer, but let me not exactly push back, but another answer that would have been related would be to say, well, if you don't like it, you can write your own version of this part of it with your own notation.
Yeah.
And again, to some extent, clearly you can do that. You can write stuff, but can I plug it into where the old stuff, the standard MathLib stuff was?
So you can write your own stuff and then write the glue theorems and rewrites and so on that will translate, and then but then it's usually going to be a pain in the neck because you've got theorems with the old way and so on. And so a better way to do it is to find the right generalization that subsumes both, and so that's the kind of, so when people refactor and rewrite, it's sort of looking, so when there are kind of different instances of more or less the same thing, you look for a common generalization.
Yeah, that's right. That's right. That's the direction this leads, which now, again, I just want to be the critical person. It's very good if you are, again, a professional mathematician, but now suppose you're coming and learning the stuff.
So this is exactly it. It makes it, this is exactly my point. This is what makes kind of, using MathLib, so hard.
And ideally,
because then things are very polished, and then you come in and look at
ideally,
this.
everybody would have a class in this in undergrad math, the math majors, and then that is an obstacle.
Right. So the question is, how do you bridge the gap from the very polished abstract APIs that the library offers, from then just being able to write things down? And we don't have a great answer for that. Maybe AI and machine learning tutorials will be there to answer questions, and we can look forward to that. So let me say something about that. So if you're coming to a field and you say, okay, I want to do something in linear algebra, what do I do? How do I figure out what the API is? Okay, so the first thing to do is, it's right here, is just to go to MathLib and look around, right? So if you're interested in linear algebra, you go see if you can find data. So things can kind of be spread out, but let's see if we can find, zoom in it, in MathLib. I don't even know where the linear algebra is. Where's linear algebra? It's in linear algebra. Okay, good. Linear algebra, affine space. I mean, even figuring out, where to start, it can be daunting. But you can always play this game. I mean, if you open this, here's determinants. The header will tell you the main definitions. You can, if you jump to you can always jump to the source file, and see, which files get imported and which things, happen earlier on. So, one thing you can always do is just go to the web pages and just browse and poke around and try to see what's there and read this. So, the documentation isn't as good as we'd like it to be, but still people are encouraged. Every file at the top should have documentation describing the main definitions, some of the design decisions behind them. Each individual definition should have a document string that explains, what it means and what it does. So that's right. So that's one thing to do. Just browse MathLib. So we're hoping that ultimately, so the plan for Mathematics and Lean was, the first few chapters was supposed to be just the basics. And then beyond that, we hope to have, chapters on different areas of mathematics that give you the first glimpse of how to do it. And so still a work in progress. We don't have, that much yet. But so, for example, just a couple of weeks ago, Patrick Massot, added this chapter on linear algebra. And so, there is a place to start and do and get documentation. I guess the other thing to do, well, there's always Zulip going and asking questions, and people will give you information and overviews. And there's Google. So sometimes formalizations happen, and people will write up papers about them and they will be published. And so if you're interested in lean, algebraic number theory, for example. So what do we have? There's a blog post about Dedekind domains and the class number on it, and that will give you some prose and overview of the definitions. Let's see, you'll find YouTube videos. So Anna actually did their dissertation on that. So you can find Anna's dissertation, which is based on a number of papers. And so that's helpful. So I guess the short answer is that it's often not easy to figure out what the API means and so on. But it's just a mixture of poking around, looking at, seeing if it's in Mathematics and Lean, looking at, nosing around the files, Googling, blog posts, going into Zulip and asking questions. Right now that's the best we have. And I think those are the general things I wanted to say.